Hello and welcome to this Python tutorial. Alright, we completed 2 steps out of 4 and today is about the third step, flattening. So this step is a crucial step to understand because basically this step consists of taking all our pooled feature maps and put them into one single vector. This is going to be a huge vector, of course, because even if we reduced the size of the feature maps and divided them by 2, well, we still have many pooled feature maps. So to summarize, we have all our feature maps in the pooling layer, we apply the flattening step, and we get this huge single vector that contains all the different cells of all the different feature maps, and this single vector is going to be the input layer of a future ANN, the ANN that we know from the previous section, that is a classic ANN with fully connected layers. Now we can ask ourselves 2 very important questions. The first question is, why don't we lose the spatial structure by flattening all these feature maps into one same single vector? And the answer is, that's because by creating our feature maps, we extracted the spatial structure informations by, getting these high numbers in the feature maps thanks to the feature detectors that we applied on the input image through the convolution step. So basically these high numbers represent the spatial structure of our images because these high numbers in the feature maps are associated to a specific feature in the input image. And since then we apply the max pooling step, we keep these high numbers because we take the max, and then the flattening step just consists of putting all the numbers in the cells of the feature maps into one same single vector, while we still keep these high numbers in this one single vector. And since these high numbers represent the spatial structure of the input image and are associated to one specific feature of this spatial structure, well, we keep this spatial structure information even in this one huge single vector. And now the second question is, why didn't we directly take all the pixels of the input image and flatten them into this one same single vector, without applying the previous steps, the convolution step and max pooling step? Well, that's because if we directly flatten the input image pixels into this huge single one-dimensional vector, then each node of this huge vector will represent one pixel of the image independently of the pixels that are around it. So we only get informations of the pixel itself, and we don't get informations of how this pixel is spatially connected to the other pixels around it. So basically, we don't get any information of the spatial structure around this pixel. However, if we apply the convolution step and the max pooling step to create all the reduced sized feature maps, and flatten all these feature maps into this huge single one-dimensional vector, then since each feature map corresponds to one specific feature of the image, then each node of this huge vector that contains a high number will represent the information of a specific feature, a specific detail of the input image, like for example the upper left border of a dog nose. And that is because this high number doesn't represent a unique pixel by itself, it represents this tiny specific feature that the feature detector could extract from the input image through the convolution operation. And therefore eventually we keep the spatial structure information of the input image. So now let's go back to Spider and let's take care of this flattening step. So as usual, we're going to take our classifier and copy it and paste it here, and then dot to introduce the add method that we still use to create this new layer, well, this huge single vector. And so parentheses, and inside these parentheses we're going to use a new function that we haven't used before, and that is, as you might have guessed, the flatten function. This is the function that will flatten all the feature maps in the pooling layer into this huge single vector. So let's input this function, flatten, spelled this way, and then some parentheses, of course, because it's a function. But then the good news is that we don't need to input any parameters here because Keras will understand that, since we're taking our classifier object, that it needs to flatten the previous layer that we obtained here after the convolution step and the max pooling step. So we're all good. We just need to select this line and execute to complete the flattening step, and everything is all good. Now this huge single vector is created, and basically it contains all the informations of the spatial structure of your images. And so now what we only have to do left is to create a classic ANN that will classify the images, and it will classify them well thanks to this input vector that contains the informations of the spatial structure. So 3 steps down, 1 more to go, and we will be done with our convolutional neural network already in the next tutorial. So I look forward to seeing you there, and until then, enjoy deep learning!